Let's dive into the world of finite automata. Finite automata are a fundamental concept in computer science, especially in the theory of computation. They serve as a simple but powerful model for understanding how machines process information. In this video, we will explore what finite automata are, their components, and how they are used. A finite automaton is a mathematical model of computation. It processes sequences of inputs and transitions between a finite number of states. Now let's break down the components that make up a finite automaton. First, we have states, denoted by Q. States represent the different conditions or configurations that the automaton can be in. Think of them as snapshots of the machine at different points in its computation. The automaton can only be in one state at any given time. Second, we have alphabet, denoted by the symbol sigma. The alphabet is a finite set of input symbols that the automaton can process. These symbols could be letters, numbers, or any other symbols that the machine can read as input. Now, let us look at the formula for finite automata. FA equals open parenthesis Q sigma delta Q0 F close parenthesis. Let's explore the remaining essential components of a finite automaton. Transition function, denoted by the symbol delta, is a crucial part. It defines how the automaton moves from one state to another based on the input symbol it receives. In simple terms, it maps the current state and the input symbol to the next state. The last two components are the start state, denoted as Q0, and the set of final states, denoted as F. The start state is the initial state where the computation begins. The final states, also known as accepting states, determine whether the input is considered accepted by the automaton. If the automaton ends in a final state after processing the entire input, then the input is accepted. Otherwise, it is rejected. Initial state and accepting states are highlighted here. Let us consider a simple example. Imagine a finite automaton that accepts binary strings that end with 0, 1. So, we need to design a finite automaton that reads a string of zeros and ones, and accepts the string only if it ends with the sequence 0, 1. Here we have three states, Q0, Q1, and Q2. Q0 is the start state, indicated by the arrow labeled start. Q2 is the final state, indicated by the double circle. From the start state Q0, on seeing a 1, the machine remains in the same state. On seeing a 0, the machine transitions to state Q1. From state Q1, on reading a 1, the machine transitions to state Q2, which is the final state. On reading a 0, the machine remains in the same state. From state Q2, on reading a 0 or 1, the machine transitions back to state Q0. There are two main types of finite automata: deterministic finite automata, or DFA, and non-deterministic finite automata, or NFA. In a DFA, for each state and input symbol, there is exactly one transition to the next state. This makes the behavior of a DFA predictable and deterministic. On the other hand, in an NFA, there can be 0, 1, or multiple possible transitions for a given state and input symbol. This introduces non-determinism, as the automaton can follow multiple paths simultaneously. DFAs have exactly one transition per state symbol pair, whereas NFAs have 0, 1, or multiple transitions possible. Let's highlight the key properties of deterministic finite automata. First and foremost, each state in a DFA has exactly one transition for every input symbol in the alphabet. This ensures that the behavior of the automaton is predictable. Since each state has exactly one transition for every input symbol, the computation path of a DFA is completely determined by the input string. In other words, given an input string, there is only one possible sequence of states that the DFA can follow. Now, let's turn our attention to the properties of non-deterministic finite automata. Unlike DFAs, NFAs can have multiple transitions from the same state on the same input symbol. This means that when the automaton is in a particular state and reads a certain input symbol, it can follow multiple paths simultaneously. In addition to having multiple transitions, NFAs can also include epsilon transitions. Epsilon transitions are special transitions that allow the automaton to move from one state to another without consuming any input symbol. This adds another layer of flexibility to the behavior of NFAs. Finite automata have a wide range of practical applications in computer science and beyond. One important application is in lexical analysis, which is a crucial part of compilers and text processing systems. Finite automata are used for pattern matching, where they identify specific sequences of characters or tokens in the input text. Another significant application of finite automata is in protocol design, particularly in network protocols and communication systems. Finite automata can be used to model and verify the behavior of protocols, ensuring that they follow the specified rules and handle different scenarios correctly. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.